Recording lecture 22. This is our part 2 on undirected graphs. So we don't have a lot of coding today, but we're going to start layering on top of the code from the last lecture. And so the familiarity with this code is kind of what you need to have in main, so to speak. So I'm going to show you the code. We're going to do a little bit of light coding today, so you're familiar with how the internals work. But our goal with this class is not to have you reinvent the wheel by writing all this code that's kind of already out there in the world. So we're going to give you a lot of this code and expect that you know how to navigate around it. Okay. So it is important that you understand how to use the code in main. Obviously, it's important you understand the algorithm that's being employed inside of the code. So we're going to take you through some major kind of first steps in our kind of recursive algorithms for graph theory today. It's going to build on top of the graph structure that we saw last time. Okay, so that's where we're going. Remember, we have homework 6 coming, about 1.5 weeks now. We have no class on Tuesday, so I'm going to be shuffling things around a little bit next week because we don't have a Tuesday. So bear with me while I kind of do that over the weekend. But I will see you a week from today, and we will jump right back into the next step in our graph kind of explorations. So we're going to probably move our homework 6 deadline from Tuesday to Thursday. So it's a week and a half away officially due Tuesday, but I'm probably going to move it to that Thursday because with this vacation day coming up, it's just going to put too much pressure on everybody. So please don't go totally to sleep on this, but I'm going to try to give you guys some extra breathing room because of this holiday. So now some of you got onto your Print Friends of Friends lab. This is a really formative lab to get to know the graph class. You will continue to be working with the graph class. So you want to do lab 21 and you're going to want to do lab 22 today. So lab 22 is kind of like print all of my friends, right? So if we start from a particular vertex in a graph, we want you to test the reachability of the graph by printing out all of your connections, direct or indirect. So it's like friends, friends of friends, etc. Okay, so that's where we're going today, and you'll see how that kind of fits in with our overall theme that will lead right into your homework 6 problem set. Okay. We'll do a quick review of the nomenclature in case you missed that. We'll go over some of the graph code again, just briefly, because we need to use it today. And then we'll look at this visual algo site and just point out some new cool areas you might want to play around with that are very helpful. So if you remember, visual algo is this graph, visual kind of tools for getting to know these algorithms. And then we'll look for reachability. So that's our lab today. Like, how do I know from a single source, a single vertex, what are all of the other vertices that I can reach? So this is kind of like all of my friends, right? So if I go on a journey starting from my home and I visit all my friends and I visit their friends and their friends of friends, that's really a recursive journey through our graph. But I'm the single source. I am the SS in this scenario, single source, and the paths are to everybody I can possibly reach. So that's why we call it reachability. So we're going to use recursion today to actually determine the reachability of every point in a graph from some single source or an initial vertex. And that vertex could be any point in the graph that I want to start from. It doesn't have to be 0 or 5 or something. It can be anywhere. So that's why we call it the single source. And SSP stands for single source path. Almost a little bit hard to say. And we're going to use depth first search to do that. If you remember, depth first search is sort of this recursive. We did it with divide and conquer, where we kind of went all the way to the bottom of like a binary tree, and then we went up and then explored another area of the tree and another. But now we're going to do it in an open-ended graph, like that doesn't have any particular root. And so it's going to require that we leave breadcrumbs so that we don't get lost in the caverns, so to speak. So it's still going to be a lot like that binary search recursion, but we're going to need a little extra data array to sort of leave breadcrumbs where we have traveled so we don't get lost in a loop, right? Because we don't want to go around recursively forever and ever and ever. We'll actually never return from our function call. So we'll look at some techniques for doing that. And then we'll introduce a brand new class, a new C++ class that will sit on top of our graph class to formalize this single source path solution. So this is a working level caliber piece of code here. We can have a very, very complex graph, and we can say, hey, I need to know all the possible ways I can get from Los Angeles to everywhere else in the country. Go, right? Figure out all those paths. That could be a lot of paths potentially, right? Depending on all the nodes that I can reach. So we're going to look at that, and that will lead us into our conversation of connected components. Connected components are all of my friends. So if I'm in a social media graph on Facebook or Instagram, and it's like, okay, I want to visit everybody and I want to visit all their friends, that's not going to be everybody on Facebook, but it's going to be a lot of people. It's going to be my own personal island of friends. And that's what we call a connected component. Okay. So how do we find all of the connected components on Facebook, right? Are there islands that are not connected to everybody else? Or is everybody on Facebook ultimately connected to everybody else? It's not a guarantee that every graph has only one component. We could have a graph that has lots and lots of components, okay? And in the extreme, nobody could be connected, and so we could have as many components as we have individual vertices. So we want to use our depth first search algorithm along with some other clever counting to actually do that kind of analysis. So two different analyses we're going to do today: finding paths and actually calculating or finding islands of connectivity inside of a larger graph. Okay, and it's surprisingly little code and it's very similar, but we're going to do it via two separate classes that we're going to build on top of our graph class. So let's real quick fly over our terminology again. Remember that sort of generally speaking, a path is just any path that connects together a bunch of vertices, okay? And it could loop back around. So a path could become a cycle if it comes back around to its origin. So any path that starts and ends on the same place, we'll call that a cycle, okay? And we'll probably not include vertices that point to themselves, right? Those are kind of a special case in that scenario. Remember that our degree is how many neighbors a particular vertex has. So we'll use that terminology relatively often. A component is this island, right? So this thing over here is a component, and we call that a connected component in a undirected graph, okay? So those are our two different components there. And we talked about adjacencies last time. Really, it's very closely related to our degree of a particular vertex, okay? So we have adjacencies K and C to vertex B. We looked at our adjacency representation. It's not the only one. We also talked about edge lists and a matrix, but we're going to go with this adjacency list, and this is going to be what we're going to use for the rest of this module in class. And it just says, hey, if you start at 0, this is how I visit all my friends. And hopefully you saw this in lab 21. You saw, well, 9 is my direct friend and 13 is my direct friend. But my friends of friends kind of, I jump over to 9 and I follow it into 8 and so on. So there's somewhat of a recursive hint here, right? If I go to 0 and then I go to 9 and then I go to 9 and then I go to 8, then I don't want to go back to 0, but I could go to 8, which would take me to 7, right? We're sort of going down these branching paths in order to explore all of the connectivity from an original single source point. So the adjacency graph is going to let us actually do that. We just haven't written the recursive code yet that will allow us to find all those connections, okay? But that's what we looked at last time. Those are our adjacencies, and you should see the similarity of that with your homework 5 that you just completed for symbol table linked lists, okay? So each one of these is a linked list. So if I say, hey, what are the adjacencies for vertex 6? You should be able to hand me a linked list and say, hey, here's the head of a linked list. Those are the adjacencies for vertex 6. And then I can independently then go travel down that linked list and go, oh yeah, I see a 5 and I see a 7 and a 13, okay? So that's what we mean by an adjacency linked list. It's going to tell us everything about a particular vertex. So remember, our node class just has an ID and a next pointer. So it's pretty darn simple. Okay, we'll continue to work with that node class. Our data members over here for the moment are pretty simple. We just keep track of the number of edges and then the vertex count. And then of course our adjacency structure, which will start out kind of with just an array of null pointers. And then as we add edges, we grow our linked lists every bucket or every kind of vertex index. Okay. So we went through that in pretty good detail. And we kind of have some fancy constructors. We have a regular one that just does that, right? And then we have a fancy one that does all of that, right? You give me a bunch of edge pairs and I'll walk through them and add edges by calling a method inside of the class. Okay. Now, for folks who have not done a lot of C++, I just want to remind you that when you call add edge from inside of a constructor, it's okay to just say add edge. You can say this arrow add edge. So for those of you who took advanced C++ or maybe are familiar with the concept of this in other languages, we could say this arrow add edge. But add edge is sufficient to call a method that is inside of the graph class. Okay. So you can feel comfortable just calling the methods like that without any kind of special other prefix on that. Okay. Now, remember our methods, our primary methods. We won't use all these today, but we're really going to focus on get adjacent vertices. So again, if I have a graph and I say, hey, give me the adjacency vertices or the adjacent vertices to vertex 5, I'm going to get back a 5. Let's 1 0 1. Let's say 2, right? So this is position 2. Give me the adjacencies for position 2. I'm going to get the head of a linked list. Okay, so it returns a node pointer. That's the head of a linked list, and then I can analyze that linked list once it's returned to me. Okay, so it's not a copy; it's a pointer to that same linked list right there. So we're going to be working with this today a little bit more. And I think we worked with that, the print adjacencies also in our lab from the other day. Okay. Now, one more thing I wanted to show you. Let's dive into get adjacencies. It's just this simple. So if someone gives me an ID for a vertex like vertex 0, I'm just going to say return ADJ VID. And that is a linked list head pointer, okay? It's a pointer to the head of the linked list at this location of my adjacency array. So now I could recursively just follow through all of those adjacencies. And that's exactly what we're going to do today. Okay, so you'll see me using this in context. So this is the class, and this is the method kind of buried inside of that class with a lot of other stuff missing from here and here. Okay. So I just want to give you that little signpost because we're going to use that today. Okay. So if we were in main, we could say, hey, I'm on a new graph with 100 vertices, add an edge from 0 to 55, add another edge from 0 to 99, and then get me the head pointer to the linked list for vertex 0, right? So that should be a linked list with 55 and 99 in it. Okay. And then we could do something with that, right? We could follow those vertices to wherever they lead us at other parts of the adjacency list, okay? Okay, so let's dive back into our graphs then, and let's just go look at some fun tools for a second. VisualGo.net has some really great stuff. And really, if you have any extra time, which I know many of you probably don't, but there is so much fun stuff they've done over here. I mean, you could study all of this and come away, you know, an expert on a lot of different algorithms. So it's really phenomenal what they have done. So first off, if you feel like you need to get kind of oriented with the whole graph language, for starters, just kind of go over to the visualalgo.net and look for graph structures, okay? So graph structures, if you dive into it, it's this orange one here, it's just going to let you start to explore what these different kind of representations will look like for different shapes of graphs. And you'll notice here, we're counting the vertices, we're counting the edges. And this particular website gives us some nice information that tells us, hey, is this a tree or not? So there's an algorithm for determining whether a graph is a tree, right? Is it complete? In other words, is there a path from every vertex directly to every other vertex? That would be a very densely connected graph. So this is not a complete graph. Is it bipartite? We'll talk about that. Is it a directed acyclic graph? So we'll talk about those in another week or so, and we'll talk a little bit about this crossing thing. But you can kind of edit this graph if you want. You may find with your homework 6 and other things, you might want to know a little bit about this particular mode. It's not the easiest one to use, but you can kind of connect these things by just dragging and then, clicking somewhere else, create a vertex, drag again. So you might want to play around with it a little bit. If you realize you made a mistake, you can just select it, and I think it's either Control or Function Delete. In this case, on the Windows, it's Control Delete. On a Mac, it's Function Delete. It's not super crucial, but it is kind of nice to have some kind of a tool where we can build some basic graphs and then go do some analysis on them, okay? So it's not a real super intuitive tool to use, but it's kind of free and available, and it's not a bad thing to have when you want to dig around a little bit. The other thing over here is you can input a graph, so you can just put in edge pairs. So this is another great way to input a graph. So you just putting in edge pairs that don't go beyond the number of vertices that you have, and our graphs are all going to be zero based, okay? So vertex 0, 1, vertex 0, 2, vertex 7, 8, etc. Okay. So this is another way for you to be able to submit and create a graph from scratch. Okay. So this is nice way, and it'll lay these things out reasonably for you. And you can reshuffle the layout just to kind of get a different picture on it. I don't know quite what their algorithm is for that. Anyway, there's a variety of these things there, and you can pull up different, somewhat canonical samples. Some of these samples have special names because they break very well-known algorithms. So it's kind of like a chess game. People come up with an algorithm, and then somebody says, oh, I got a graph that puts your algorithm into an infinite loop. Haha, so it finds the weak points of somebody's algorithm. So some of these graphs are very useful for testing against well-known algorithms that try to solve hard problems. This is what's called a bipartite graph. Bipartite graphs we'll talk about have sort of teams or pairings, right? You have people on one side and jobs on another, and you have preferences. This person over here would like to do these jobs. This person over here would like to do these jobs. Okay, then let's figure out how we assign people to specific jobs to maximize or minimize something. So bipartite graphs are used in sports analysis for pairing together of teams in competitions, for doing betting analysis, for doing optimizations. And we'll study some bipartite graphs toward the end of the semester if we have time. So it's a subclass of a variety of graphs, very interesting kinds of things you can represent with that. So anyway, good place to kind of go for interesting things. Now, as to these definitions, so complete, again, it means true if every combination of two vertices are connected. So if I have n vertices, that would be a very dense graph of n times n connections. Okay, so that's a pretty dense graph, not very realistic in the real world. Directed acyclic graph. So we are dealing with undirected graphs right now. So until we get to graphs with arrows for edges, we're not really going to be talking about DAGs. But if you go out into the software world and start working in a situation where you're building something like a 3D modeler or something that analyzes network traffic or some data structure like that, very often you hear people talking about a DAG, a directed acyclic graph. So it means there are one-way relationships and no cycles inside of that particular graph, okay? So if there's no directed cycles, we would refer to that graph as a DAG. Now, a tree is a subset of a DAG. right? So it is a rooted DAG, a rooted directed acyclic graph. So that's really what a tree is, right? So it's kind of redundant to say, a tree DAG is a DAG by definition, but it happens to actually have a dedicated root to it. Okay? And then bipartite, as we said, splitting the vertices into two groups, essentially such that every edge goes between the two groups and never within the same group. We never have an edge connecting two players on the same side of the field, basically. Okay. That's what we mean by bipartite. And we'll study bipartite graphs a little bit as we go forward. Okay. So that's some of our kind of primary language. The other thing, I think we kind of did a little bit of this, but you may want to practice again, make sure you're comfortable with this tool, adding and deleting and connecting some nodes, because you may need to build some special purpose graphs to kind of test out your work. Okay. So we'll kind of fly over the top of this second practice, but you may want to go back and see if you can kind of notice how the adjacency matrix, the edge list, the adjacency matrix, the edge list, and the adjacency list all basically capture the same information for every particular graph. It's just different ways of representing it in memory. Okay. And again, we're going to be working with the adjacency list. Okay. So you should be able to turn a graph into a tree by essentially deleting enough nodes, right? And notice also, let me jump back over here for a second just to show you. The other thing to be aware of with this website, it's sometimes not easy to know. We are in the directed unweighted graph category, okay? So you can go into the undirected and weighted. So now our edges have values, okay? So if I go into and edit, I can pick and I can change the values on some of my vertices. Whoops, I didn't mean to create that one. But basically, weighted is the UW, unweighted, undirected is UU, directed, unweighted, and directed weighted. These are the four categories of graphs we will work our way through during the next couple weeks, okay? And all the way back in the Visual Algo top level page, there's a lot of different things we can do with graphs. So we're going to look here at traversals here in a second. So let's take a look at graph traversals for a second. Okay. And by the way, feel free to read any of these. They're actually pretty quick reading. They're just little short highlights. They give you nice insights. They give you a little summary and some, little questions from time to time. But essentially, if you have a graph on the screen and you want to do a depth first search from a particular vertex, let's start with one, for example. And I'm going to actually go, am I in the directed? I'm in the directed graph. So I would rather be in an undirected graph, but let's just show you while we're here. That's our source, right? We're going to try to visit everybody we can. And that's pretty much it, right? Now, if I start from over here instead, so let's start from a source vertex of 0 and go there. Our direct depth first search will recurse all the way to the bottom, back up, back up, back up. Now explore the other side of the tree and then realize we've already visited 3, right? So that's really what we're going to do today. And we're going to do it in an undirected graph. So we could end up going around in circles if we're not careful, right? So that's one of the things we kind of got to be aware of. So anyway, there's great tools here. And again, the primary ones right now are going to be this graph view, graph structures, and graph traversal. And you'll notice in graph traversal, there is a depth first search, and there's something called a breadth first search. And you might remember the breadth first search from our binary search tree discussion and our heap arrays when we talked about those. So we'll come back and review all those for you. But these are just good tools for you to be aware of. And when you need to kind of explore some of the graphs that we're talking about. Okay. And again, here's just a little bit more on the bipartite graph. Again, if we can arrange the vertices on paper, so to speak, and some people talking about them as red team and blue team, right? All the reds on one side, blues on the other. And the edges that connect them do not connect all on the same side, then we would say that's bipartite. Okay, so these are two bipartite graphs, and they represent pairings. Some of them have cycles, but as long as the cycle length is even, we would consider that still to be a bipartite graph. And we'll dig into those a little bit later, but these are great structures for analyzing pairings of things that might happen, okay, between two things, maybe people and jobs, or you have preferred roommates, or you have preferred rooms that you want to be put into, and we got to figure out how to optimize everybody's choice, right? Everybody wants to get into a particular dormitory, but not everybody can get in there. What's your first, second, and third choice? We would use a bipartite graph to help us solve that particular problem. Okay. So we'll come back to those and take another look at those as we go forward. But let's talk about reachability now and get into our depth first search algorithm. Okay, so reachability in undirected graphs. Thank you. First off, we just have to choose where do we want to start from. So you can start from anywhere you want in a graph, okay? So the vertex that we're picking is our single source. So that's our SS, or single source. So if I had a from vertex, right, and I was trying to get to vertex 3, what are all the ways that I could get to vertex 3 from every vertex in the graph, right? So let's map a path from 0 to 3. And sometimes there's going to be multiple paths. So we can all kind of see I can go directly from 0 to 3. So that's a pretty short path. From 1, I got to go through 0, right, to get to 3. So that's not the shortest path, right, to 3 in the graph, but it's pretty short. 2 to 3, there are two ways to get to the 3. I could go through the 5, or I could go directly from the 2 to the 3. Okay, so that would be the shortest path from 2 to 3, of course. Okay, and 3 to itself could be considered a path, but usually we ignore that because it doesn't really help us with anything. 4 has no path to 3. So sometimes we will indicate that with some special value like a -1. Okay, and of course, 5 can go directly to the 3 or through the 2, just like the 2 is going through the 5. Okay, so looking at this analysis, I would say, oh, okay, there are 3 paths that are the same length to get to 3 from other places in the graph. Okay, now that information might be useful or might not be useful, but that's kind of the analysis we're going to be doing. It's like, I want to get to 3. What are all the ways I can get to 3? And maybe which ones are the shortest, right? That's another interesting layer to that question. Okay, so this tells us about the reachability of this entire graph to a single source 3. Okay, and it also tells us, it says if there's a path, yes, it's reachable, right? So 4, not reachable. If there's a path, it's reachable. And what's the path? Those are 2 different pieces of information that we're going to try to get today. Okay, and notice that the path is sort of backwards toward the source. So the way we're going to do our depth first search recursively is going to build our path in reverse. We'll show you what we mean by that. Okay, so it leads back to the source. Now, it may be the shortest path, the path we find, but it may also just be one of the many paths back to the source. Okay, so the single part is, we're just analyzing vertex 3. We're not analyzing how to get back to everything else. We're just analyzing how to get back to vertex 3. Okay, so if we can find any path, we'd say, hey, is there any path from 0 to 3? Yes. Is there any path from 2 to 3? Yes. Right, there is. What is that thing? Okay, so we'll look at that here in just a second. Okay, so depth first search is what we're going to use. And let's consider maybe a familiar situation like Pac-Man. So many of us played something like Pac-Man, or maybe have heard of Pac-Man. Often these things are represented as undirected graphs, right? All of the junctures between the hallways are little nodes in our graph, and we have connectivity. And our little Pac-Man or the ghosties could potentially travel from little juncture to juncture, right? So we might want to know, is there a way for the ghosties to get to the Pac-Man? Okay. And ideally, the ghosties want to figure out what the shortest path is. So we'd like an algorithm, first off, that says, can the ghosties reach the Pac-Man? Probably they can in this particular game. And then secondly, which is the shortest path? And maybe that's the one the ghosties are going to try to take, right? And then we, of course, as the Pac-Man, have to get away. Okay. So we would like to be constantly updating some path information that says, okay, if I'm the ghosty, like what are all the ways that I can get to the Pac-Man? Because the Pac-Man keeps moving. So I got to analyze that and then make some decisions based on that. So our adjacency list is going to be crucial in solving that algorithm. So let's say the Pac-Man is position 0, okay? And I want to find out all the pathways to get to position 0 from inside of my graph, okay? So we're going to start our depth first search at vertex 0. That's our Pac-Man. That's our single source point of interest. Now we need to, because this is not a tree, we need to mark that somehow as visited, because we don't want to end up going in circles forever, infinitely, in our recursive loops. So we're going to need a little array or some way of saying I've already been here to drop a breadcrumb. So very often we just create an extra little array with a Boolean value for every vertex in the graph to say whether it was visited or not, okay? So initially, nothing's been visited, okay? So if I start at vertex 0, I'm going to mark that thing as visited, okay? And I'm going to recursively follow its adjacencies, and every time I jump to another adjacency, I will mark that one as visited as well, okay? So as we travel down using our adjacency list to guide our recursive traversal, we will drop breadcrumbs in this array up here so that we don't get lost in the maze going around and around, okay? But along the way, we will essentially discover whether or not all of these vertices are reachable. So let's kind of go through this a little bit with some animation. So we're going to mark that one as true, right? So we start our recursion there, mark it as true. The first adjacency we have is 1, right? So we're going to jump on over to its linked list over there, mark that as visited, right? And then we're going to follow its path. Now notice we didn't double back to the 0 here. We just went to the 2, right? Because the 0 was already visited. I don't want to go ping pong in between 0 and 1 forever, right? So I'm going to skip anybody in my adjacency list who've been visited, recursively go to the 2, mark it as visited, and continue with its recursive traversal, right? So we're getting deeper and deeper in our recursive traversal. We say, okay, 2, I don't want to go back to 1 because that's where I came from. So let's go to the 3. Okay, now we're over at the 3, okay? And we mark that as visited, and on we go. We just keep following the unvisited vertices in our adjacency list. And over time, we kind of hit a dead end, right? So if I follow 3 and then I go to 10, 10 takes me to 9, 9 takes me back to 10. That's the end of my recursive journey so far. Okay, so 9 is as deep as we go based on that particular adjacency list. So it's time to unwind in our recursion. So, and we'll look at the code for this in a second, but it's helpful to imagine this like us in a cave system going deeper and deeper and deciding, oh, can't go any farther. And then I go back all the way to the first place I didn't explore a leftover path. Okay, so number 1, all the way back here is the first place we never explored an extra path, right? So we're going to go back. I think that's correct. Or was it a 4? My animation might be. Oh, yeah. The 4 was what we wanted to do, right? Okay. And then we can't go to the 1. So we follow down the 5, right? So because we came down the 4 first. I think that's how we got there first. Anyway, I don't want to get too lost in my own maze of connectivity. But essentially, we're just following marking visitation. And notice that at this point, the 8 has not been visited, okay? So if I just want to know about reachability from 0, I'm going to stop my algorithm right there because that answers the question. Everything here is reachable from 0 except for 8. 8 is not reachable. Okay. So we can kind of see that from looking at this graph. But if this were a massively complicated graph of underground pipes or electrical wires or internet traffic or whatever, no one's going to be able to know that, right? Or a Facebook graph with 1 billion people in it. So here we found all of our friends. So this is really what we're kind of going to do in our lab today, is just find all of the reachable friends for a particular vertex. In this case, I did it for vertex 0. Now, our other algorithms will continue the journey, and we'll talk about that in about 5 or 10 minutes here by, doing a separate analysis for whatever's left, right? But for reachability, that's all we really need to do. And this tells us reachable, 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 not reachable for vertex 0, right? This is analysis just for vertex 0 as a single source, okay? So let me pause there. See if anybody's got any questions. Yes.
So you went from 3, you went to 10, but could you go straight to 4?
So if, yeah, you could have, and that's a great question. But if you think about it, if I built my adjacency list this way, and I go to, let's see what we did first. Let me go all the way back to the beginning. Yeah, this is a really good question. So we go to 1, right? 1 says go to 0, but we've been there. I'm going to mark those out, right? So we've been to 0, right? Okay. Um, and we've come to 1. We haven't gone through 6 yet. So I'll mark out this as well. So we came to 1, we went to 0. Now we're going to go to 2, right? So we'll go to 2. So I'll mark out the 2. So now we're over here. I don't want to go back to the 1. And I go to the 3. So I got to the 3 first, not the 4, because I jumped here from the 2. So I could have got to the 4 first if our construction order had put the 4 here and the 2 there, right? So if the 2 and the 4 were swapped there, then you're right. I could have gone to the 4 first. But if I'm blindly following the adjacency, and remember, this is a linked list of nodes, right? Then that's where we go, right? We're just sort of following it based on construction order. Now, would I get a different answer if I had swapped the 4 and the 2? No, that's a good thing, right? If the construction order is different in terms of reachability, I would still end up knowing that these are all the things I can reach, okay? But it could change other things. By changing the construction order here, and that's a really key and subtle point, we might get a slightly different answer for some of our other algorithms that we're going to actually be talking about, okay? Okay, so good insights. So that's our reachability. That's kind of first level stuff. The next thing we want to know is, well, how do we kind of find all of the possible paths for those ghosties to reach Pac-Man at 0? Okay, so that's our next thing, right? So let's kind of jump into that. So here, what we're going to do, in addition to our was visited, we're going to add a from vertex. Okay, now here, we're not going to record every path back to 0. We're just going to record the first path we find. Now, this is not the shortest path, and it's not all the paths. It's just a path. So this is not your like grade A triple best solution for the ghosties to find the Pac-Man. It's just saying, hey, find any path from the ghosty back to 0 using depth first search. So it's somewhat basic algorithm, but let's kind of augment what we did last time. So every time we visit something, let's write down how we got there, okay? So let's trace it through here, a little less animation. So 0, I follow the adjacency graph and I go to 1 and I write down how I got to 1, okay? So 1 was reached from 0. Okay. And I follow the adjacency graph for wherever it takes me. Let's say it takes me to 2, and I write down how I got to 2. Okay. So I'm sort of building a backwards path that tells me how to get back to my single source vertex 0. And I'm doing it recursively. So as I dig deeper, I'm leaving a breadcrumb trail of where I visited. And you could kind of say I'm writing a note on the wall that says how I got here. Okay. So it tells me how to get back to where I came from. Okay. So by the time we recursively visit everything we can reach, we now have a path from every vertex back to 0. Okay. So we've done a comprehensive analysis on the entire graph using depth first search and found all of the reachable parts of the graph, all of my friends, right, and their friends, and how my friends are connected to me by tracing backwards to me, okay? You could also think about, doing this for ancestry types of stuff. Like, how is someone related to me? Okay, let's just trace it back through, cousins and whatnot, right? So, but here we're just working backwards. So if I said, hey, can you reach 0 from 10? You'd say yes. And how do I do that? Well, I go to 3, 3 takes me to 2, 2 takes me to 1, and 1 takes me to 0. And 0 goes nowhere because that's my single source, okay? If I say, how do I reach 0 from 8? You would say, can't do it, right? Because there's a -1 there. So it didn't get reached and there's no path back to it. Okay. So we're going to do this pretty elegantly in a relatively small amount of code. And again, it's just an analysis for position 0. So this is where Pac-Man is, and the ghosties need to figure out how to get back there. Okay. So we need 2 arrays. Those arrays are going to be, one of them is going to be an integer array, and one of them is going to be a Boolean array. And they're going to be the same size as the total number of vertices in our graph. So if we got 1,000,000 vertices, we need 2 times 1,000,000 extra positions. So in terms of space analysis, this particular algorithm requires 2n, we would say 2n extra space to save up this information, okay? So that's our analysis, okay? And we can answer any question we want. If was visited, position number equals true, then we know we can reach it, and we have to walk back in a while loop to get back to our source vertex. Okay? The cool thing is that once you've done this analysis on a very large graph, the cost to answer these questions is constant, right? Because we know instantly. So we pay an initial cost, which is our depth first search cost. And then we have the analysis for all paths back to 0, if that's what we did for an analysis. It's not all paths back to everything. It's all paths back to 0, which is our single source vertex. Okay. Okay. So a little bit of extra memory, but once we do the analysis, we can answer lots and lots and lots of questions. If the Pac-Man changes position, we have to do the analysis again, right? So that's not the best algorithm for fast moving Pac-Mans. So a lot of games use a slightly different algorithm for that, but this is just us getting our feet wet, right? So it's kind of the first most basic approach to do it. And as we discussed briefly with that question we had, construction order of adjacencies determines if we have which of the paths we get, right? We're not getting all possible paths back to 0. We're just finding one of them, okay? Which is a little bit of a subtle point here. We can't store every possible way to get back to 0 from number 9, or let's see 3, right? Because 3 could go back to 0 this way. It could go back to 0 this way. It could go back to 0 this way. A recursive traversal is going to really only end up picking one path. And the path that it picks is kind of based on the construction order, and it's a little arbitrary. But it's not wrong. It's just one of the possible paths. Okay. And again, it's a basic algorithm. It's not the, the sterling gold best possible way to do that. Okay. So how do we encapsulate this in code? It's not a lot of code, but we're going to put it in its own class. So we have our graph class. Graph class is kind of done. We've kind of, wrapped a bow around it. We don't really want to change it. So we're going to make a separate class that can study the graph and do the path analysis. So we're not sort of polluting our graph class with stuff we don't necessarily need. So this is just the way we're doing it. You could, out in the real world, combine these two things together. But here's how we're going to do it. We're going to have a constructor for our paths class. I should call it paths plural. We're going to give it a pointer to a graph, right? So we can follow the pointer to the graph information. And we're going to give it our single source vertex. Where's our Pac-Man, right? Which one of those vertices do we want to analyze? And then we're going to have one primary method called DFS, where we traverse that graph from that initial position, okay? And that's really just about all we're going to need. Now, the has path to is just checking our was visited to say yes or no, is there a path? And then get path is sort of walking backwards down that from vertex array we looked at to print out that. But most of the hard work is going to be done right here, okay? So we'll look at that code together. Now, we will eventually see that a breadth first search is a really powerful way to find the shortest path, not just any path, but the shortest path. So that's really the gold standard. Really, if we want to find the shortest path, we'll need to write some code to do a breadth first search. But we're going to start over here today, and we'll come back to BFS on another day, okay? But that's really kind of how most interesting problems are solved. So here's our path class, okay? This is our strategy, right? We're just finding a path to 0 or something if it exists, okay? And we'll store that analysis in our two arrays, and then we can, study those. So here's what our whole situation looks like. I got a node class. I got my graph class with a big old adjacency list hanging off of it, and then a brand new thing that just has a graph pointer passed into the constructor with the root ID. We will store that single source root, how many things we had, and we will allocate a size n array for was visited and from vertex. So that's what our constructor is going to do. And then it's just going to call our depth first search function, and it's going to fill out all of the stuff for us, okay? That's what our path class is going to do for us, okay? It's going to use a pointer to that graph. It's not storing the graph inside of the path class. It's just holding on to that pointer so we can jump over there and then grab on to one of these things over here and do some recursive traversal using that, okay? So it's just a reference or a pointer to that thing, okay? So it's not storing it inside of the class. Okay, so here's the code. So paths has a root ID, number of items in the graph, a pointer to what we are going to allocate dynamically, because we don't know how many things we need yet until somebody gives us a graph, right? So then our constructor is going to say, hey, you gave me a G. I'm going to say, how many vertices do you have by calling its vertex count method, putting it in my n. I'm going to pull the vertex ID here into my own root ID, right, up there. So that goes into there. I'm going to dynamically allocate a Boolean array size n and our path ID number array called from vertex, okay? So that's the first part of my constructor, okay? And then I'm going to initialize everything. Now we could get fancy in C++ and make sure that these initializations are all done as soon as they're created, but I always like to just make it really clear. We're going to go through, set everything to false, -1, and now we're just going to do a depth first search, right, with a little secret sauce inside. So we give it the pointer to the graph and where we want to start, and that kicks off the process. Now notice that this is going to be updating this during recursion, okay? So as we are recursively calling ourselves over and over again, we're going to be taking notes over here, okay? So that's what we're going to do while we're recursing inside of that depth first search function. So, and then there's the methods, right? Here's the implementation. So this is me calling it inside of my constructor. So by the time my constructor is done, it will have finish the analysis here. And then we can come over and ask questions about it, okay? So it's construct and then ask questions. And we'll take a look at all this final code once we get it up on the screen here, okay? So there's my path constructor. There's the heavy lifting, right? DFS initializes those two arrays, and then we'll have that, individual method implementation, okay? So there's our path constructor, and there's us calling DFS, okay? So by the time it's constructed, the hard work is done. That's the really kind of nice thing about it, okay? We're ready to answer questions. So let's take a look at that particular method. So DFS method inside of the paths class. This is a very C++ way of saying, hey, I'm talking to you about the DFS method inside of the path class, paths : DFS. That means this is a member of this class right here, okay? So that's all we're really saying. So there's our kind of starting and ending. We're inside of the DFS class. And what we want to say is, okay, if you want me to start here, I'm going to set that to true because I'm here. I'm at VID. So was visited VID gets true. Okay. And then I'm going to say, hey, go over to the graph and get the adjacency list. So we're going to call get adjacent vertices to get the head pointer for this VID, right? That's our jumping off point for recursion. So it's a linked list of a bunch of nodes for the adjacency list for VID, okay? Which let's assume was 0, for example. Okay, so that's top level recursion. Now, I'm going to say, okay, let's just walk down the vertex list. Get a temp vertex starting at the head. As long as it's not null, inside of the for loop, we'll just keep going next, next, next. You could do a while loop here. I just did the same thing with a for loop, okay? Head vertex, keep going while it's not equal to null. When you're done, move it forward. So what do we want to do in there? Okay, if this vertex that we're pointing to is not visited yet, then we can recurse, right? We can say, okay, I will drop down a level and follow that vertex from the linked list, okay? Give you guys a moment to soak that up. So I'm at 0, and let's say it's connected to 1. So I pull 1 off the vertex list, and I recursively say, okay, do that again, starting from 1. And then that recursive level picks up the adjacency lift for 1, and we start drilling down recursively. But we got to come back. So when we finally hit the bottom of that search, we go around the loop and get the next adjacency in 0's adjacency list, okay? So we come back, but before we do that, we're going to record that we got to this vertex TV from VID, 0 to 1, right? So that's going to be our second little update. And that's it. And we'll go fill in this code together, but that's super cool. It's really cool. It will eat up any graph recursively and fill in all of the path information for us and establish reachability for everything in the graph, whether it's 100 things or 100 million things, okay? And of course, it's going to go pretty deep into recursion. So it's going to use a bit of memory actually doing this. So if the longest path in your graph is 8 long, you're going to be 8 levels of recursion deep. But if the longest path in your graph is 100,000 edges long, you're going to be 100,000 levels of recursion deep. So there is some practical limit to what we can do recursively here, okay? But it's the idea that we're most interested in. Okay? Let me pause there, see if you have any questions before we dive into that part of the code. Still doing okay? All right. Okay, so let's see if we can finish this part of the code. And it's a little bit of a heavy lift, so we'll take some time with it. We're going to try to create this graph right here. And then once we do some reachability tests, And we could say reachability from 0, right? Obviously, we should not be able to reach 0 from 5 or 6. So our analysis should support that. And this pair listing 0, 1, right? 0, 1, 0, 2, that's just our edges. And most of the code I write requires that we enter a -1, -1 at the end. Now, I know Program IZ is probably going to be a little hard to navigate at the bottom of the window in the output area. So we'll do our best to kind of get through that. Okay. So let's take a look at the code, and then we'll do some queries to see whether or not we got it right. Okay. So shortcut for all this stuff is to always look for TODO. Okay. So find TODO. Okay. So we're going to jump down here. We're in the DFS, right? So here's our path class. Here's our couple emergency checks to make sure our, the VID that we're searching for is in range. So that's just some, safety valves. Here's initialization. There's me calling the recursive call. Make that a little bit bigger. Okay. I don't want to make the ads so big that I can't see anything, but there's the graph class. There's the recursive call. Here is the recursive DFS. Okay. So sorry for the jumping around there. Okay. I'll stop that. Okay. So was visited, VID gets true. Okay. Was visited, VID gets true. So we're at vertex 0 or whatever. And we're going to say, yep, I've been there. Okay. Now call the graph, get adjacent vertices. That's the name of the method in the graph class, and I want to get the adjacent vertices for the ID. Okay. Now I've got kind of a head pointer, and I'm going to say temp vertex equals the head pointer. Keep going while temp vertex is not equal to null. And then I'll say if not was visited, square bracket, TV arrow, VID. Okay. So this is a node pointer. So I want to reach inside and check its ID for the adjacency linked list. Say if it wasn't visited, then let's go crazy, right? G and visit TV arrow VID, right? And when we come back from that deep recursive journey, just mark how we got here, right? So from vertex for TV VID was, or sorry, TV ID, my bad. It's not VID, it's ID. I forgot what my data member was in my my node, right? So TV ID comes from VID, okay? So we're recursing down on VID, checking all its adjacencies, and that's kind of it, right? And everything else I think here has been written. Let me see if we got any other to-dos here, and then we'll give it a try. Okay, so we did that one, did that one. I think that is everybody. Okay, so let's see if I created any mistakes so far. Okay, all right, so let's zip back a little bit. Okay, so how many nodes do you want to create in your graph? Okay, so let's create 7, 0 through 6. Okay, so there's our 7. Okay, so it's just reminding me that I can build a graph. This is the graph. So let me show you guys a shortcut for this semester. Anytime you see me do this, you can just copy it and paste the whole thing there all in one line. And the input processor for C++ will process those as if you put them in on separate lines. So it's going to work to give it the whole graph all at once or pair by pair by pair. Okay. So once I do that and hit return, we now have our adjacency list. We got to scroll all the way to the bottom to see it, but there's our adjacency list. So it's saying, hey, which vertex between 0 and 6 would you like to study? So I would like to study connectivity for vertex. So we want to know which one can reach. I'm going to build my path class to vertex 0, right? So I've only built the graph. Now I'm going to create the path class. Okay. So now it's built the adjacent vertices for the path class. And it's saying, which do you want to test against vertex 0? Okay, well, let's look at our picture. Can we reach vertex 0 from 4? Okay, so I'll say, can I reach it from 4? Okay, and it says, yes, there's a path from 4. Okay, so it's really just telling me yes or no based on the code that I've written. But we could get more data out if we wanted to. Let's test from 3. Okay, so 3 should reach, right? So 3 is reachable. 5 and 6 should not. Okay, 5, that's a no. 6, that's a no. Okay. Okay, so a lot of output there, but we're really just exercising the DFS call. Okay. And this is important to be able to wrap your head around. So let's go to the code here so we can just talk about this for a minute. Okay. So we're reaching into the graph to get a head pointer. And then we're traversing down, then we're traversing down that linked list for that particular VID at this recursive level. But then when we do this, it's like dropping down in an elevator to the next depth of recursive level with a different adjacency list, and on and on and on. And we keep popping up, wrapping around, popping back down again, popping up, wrapping around. So we have to envision a recursive tree where we are visiting every unvisited node in that graph, kind of like we did with our Pac-Man game, okay? One of the skills we want to develop in this class is the ability to look at that kind of recursive code and either with pencil and paper or our brains imagine what's happening in our graph, okay? So that's the skill we want to get better at, okay? Because it's super powerful once you understand how to kind of wield that in code, okay? Questions before we move off that? Okay, so hang on, we're 2/3 of the way through, okay? So, and just remember, our path has to path is really just sort of returning whether we visited that, right? If we got to that thing, then we know it has a path. So that's just a simple yes or no question. Did you get there from some particular VID? Okay. So if I'm analyzing reachability from 0 and you give me 7, that means yes, I can reach it from 7. That's all we're really saying there. Okay. So that's just a little side thing. So if P dot has path to VID returns true, then yes, we know we can reach it from 0, right? Because that's what we're analyzing. P is the analysis of our path to 0, paths to 0. Okay. Okay, so that's our has paths to. Okay, so we can determine if a path exists. There's no guarantee if the path we found was the shortest using depth first search. When we move to breadth first search, B, then we will see and we'll study why that's going to give us shortest path, which is usually more valuable. Okay, and there might be lots of paths. We only found one of the possible paths back to 0 from a particular vertex. Okay, so we got to analyze every time Pac-Man moves. We got to do the analysis of the path all over again. Okay, so that's a really key thing. So you're going to want to go back and spend some time on that. Now we're going to tweak that a little bit to solve one more problem today, and then we'll I think we'll get ourselves into lab here pretty quickly. So connected components are the islands that represent connectivity. So no, if you remember, we never really could visit everything when we did our first depth first search in that first example. We never really got to vertex 8, right? So depth first search is kind of going to tell us for the island that we started on, who's not on that island. So if I start at 0 and I do a depth first search through all of this stuff, right? These are all going to be visited and these are not going to be visited. So I could mark all of these as part of island 0, right? And then I could start over here and do a depth first search and mark all of these as part of island 1. So island 0 and island 1 would be what we call our two components. Component 0 and component 1, that's two components, okay? So we're going to use our depth first search, and we're going to keep track of an additional piece of information, which is which island are you on? So once we've explored every particular vertex and visited everything, we should have marked who belongs to what island. And this is a really powerful algorithm for finding connectivity in social graphs, electrical systems. This is what homework 6 is all about. So all those story problems in homework 6 are just different ways of asking you questions about connected components. And what we want to learn in this class is, how do I recognize the tools that I have to answer that question? So homework 6 is, the easy answer is connected components. Okay, so yes, we can answer those questions with connected components. You just have to do a little bit of extra work around the edges. Okay, so these are our islands of connectivity. Okay, and they're in the same graph. Okay, and we're just going to determine whether we can reach them all via the depth first search. Once we do the analysis, we'll know instantly in constant time whether or not they are connected. We'll just be like, hey, are you in the same component that you are? No. Okay, well, then you're not connected, right? That's super powerful, okay? So it's used in seed fill algorithms, right? So if you have ever worked with painting programs and we want to fill in everything that's connected in a fill color with something else, those are often done with something like a connected component problem, right? Following whether adjacent pixels are of the same, background color or something like that. We can do a seed fill that way. There's lots of different reasons why we might want to use these connected components. Okay, so we're going to, once again, build a special class that analyzes a graph without polluting the graph itself. And we're going to need a integer in our special connected component class that keeps track of how many components we have. Okay, and when we get the ID of a component, it's just going to be island 0, island 1, from 0 to at most n-1 islands. So you may recall I said if I give you 100 vertices with no edges, that's 100 islands. So every vertex will belong to its own island. But that's not usually what happens. Usually there's connectivity and we have much fewer islands than we have people in a social network, for example. Okay, so the most we'll get is n-1. So we should be able to say, hey, are you and I in the same island? Yes or no? And that's a really important question. That means we're not connected by electricity, or, if I'm Yoda and you're, somebody out there in the galaxy, we can tell whether or not you're part of the good guys or the bad guys. So that's what that connectivity test is all about, okay, in the context of homework 6. But we got to do our depth first search first to answer those questions, okay? So now let's just talk about connectivity again for a second. So we say if A is connected to B, then B is connected to A. So we say that's a symmetric relationship. Okay? It's kind of mutual in undirected graphs. If A is connected to B and B is connected to C, then A is connected to C, transitive. Probably heard this language in math class before at some point. So a connected component in graph theory is referred to as a maximal set using those laws. So we're going to do it with a depth first search, but sort of like theoretically, we'd say, give me the maximal set of all things that are connected to A, for example, right? And so that's what we're doing. So here's how our data is going to be organized. So for every vertex, we're going to have an additional array that says what island it belongs to. Now notice vertex 0 is in this green island that is, we're going to call island 0, okay? So everything that's green belongs in island 0, okay? Everything that's yellow is going to belong in island 1. We don't really care so much about what number it is. It's just that when we have the same component ID, it means we're on the same island together, right? And our depth first search is going to be responsible for assigning those numbers, okay? And we'll show you real quick how that's going to happen here, okay? It's going to look really similar to the path class, okay? So we had our was visited. We're going to do that again, but now we're going to have a component ID integer array. We're not going to do paths for this particular analysis, so we don't really need that information. We just want to know, are they in the same island or not? Okay, so we're going to need that array, and we'll call that our component ID. And we're going to assume initially that everybody's on their own island alone, right? So negative 0 is one way of saying I'm not on any island. But probably if they were unconnected, it would be 0, island 1, island 2, etc. But initially, nobody's on an island. We'll use depth first search in our adjacency list to visit everybody, and we will keep count, okay? So anybody we visit the first time is going to go on island 0, okay? Depth first search, depth first search, depth first search. Okay, everybody's going to get marked with the current island number, which is 0, okay? Then I got to go searching for anybody who hasn't been visited. Oh, this guy hasn't been visited. Okay, now we're going to move to 1. Okay, now you're on island 1, and we're done. Okay, so we're going to do multiple depth first searches to try to find all of the different islands. Okay, so let me clear this up and do my little animation here, and we'll jump into the code pretty quickly. And we're not going to make you write this code. We're just going to show you the code for time's sake. So between each successful depth first search, we have to increment the component ID and go looking for any vertex that has never been visited before. So in this case, there's 2 islands, and we'll look at 0, and then we'll be like, oh, well, I visited 1 and 2 and 3 and 4 and 5 and 6. Oh, I didn't visit 8. Okay, let's do a depth first search there, right? And then we're done. That's how that's going to go, okay? So what we'll end up here is doing this, right? Everybody goes in 0, right? And we follow 5, 6, 7, and we're done. Okay, we've returned up to the top level of recursion. We couldn't find anybody else. But is there another vertex that hasn't been visited? Yes. So let's do a depth first search starting at 8 and explore everything we can find there. But we have to increment that counter before we do that so that we assign a unique value for that component to 8, right? So now 8 ends up on that other island, okay? And now we can answer connectivity questions in constant time. Who's connected to whom, or are they connected? No path information, it's just connectivity, okay? But sometimes that's a really simple and important answer, okay? So we have 2 islands in total. They are island 0, island 1, okay? And comp of 8 equals 1 means 8 belongs to comp 1, component 1. All right, so let's take a look at our class, and we'll get this thing wound down here pretty quickly so you can kind of play around with your lab or whatever you got to do. Component class, here's our was visited. Keep track of total components. Here is our comp ID array. Here's a pointer to the graph that is given to us. So somebody gives us a graph, and this is just a little bit of a debug flag to help with some debugging code. But I'm going to get the vertex count, allocate the was visited and the comp ID arrays. I just wrote a little function to loop through and initialize these things here rather than have the code right there. And then we're going to go through every vertex in our constructor, okay? If it was not visited, we're going to recursively do our little dance, right? We're going to say DFS CC for connected component. So this is a different DFS because we're in the connected component class. Here's your pointer. Here's the vertex I would like to start from. Try to find all of my friends. And when you're done, increment the number of islands and go around and try the next vertex. Now, probably the next vertex was already visited. So we're just going to keep trying and trying and trying until we get to that number 8, for example, and then we'll recursively follow it around. So the tricky part of this is that we are trying to call depth first search a bunch of times, but we probably will only call it a few times because we'll probably, like at the top level, because we only have a few top level islands. Okay. The first call to DFSCC is going to mark that many of these things were visited. And so when we pop back up from recursion and wrap around, we probably are going to find that a lot of these things have already been visited, but not all of them, right? So we'll increment our component and drop in again, and the process continues, okay? So that's our DFSCC in our connected component class. Let's see if we can zoom in on the code for this. So there's my init. So this is nothing special. This is just me going through and marking these arrays with initial values. Here's our DFSCC. Notice the similarity to what we did last time. We come in, we mark it as visited, right? We're going to put it in a particular island. So this is our component count. It's currently 0. So this goes into island 0. I get the adjacent vertices for VID. I follow its linked list. And if it wasn't visited, then I will drop in again, right? Even deeper. I'll say, take this ID, and the process recursively continues. Eventually, we unwind all the way to the top back in our constructor, and we increment and go around and try to do it again, okay? Sometimes succeeding, sometimes failing, okay? Whoops. So that's the magic part of connected components. Same depth first search idea, a little teeny tiny tweaking of different data, keeping little different notes than we did for our path, okay? But super powerful. The vast majority of algorithms we'll study in class from here on out are going to be depth first search or breadth first search type of algorithms with little tiny tricks along the way, okay? Questions on that one? All right, so let me see if I can get us to the end here. So just for context, okay, I won't go into all of them, but let's look back at homework 6 and what we want to do in one of these adventures. You're going to take this finished code from this practice problem. Now, it's going to be in your homework 6 Canvas page, so don't go grab it from here. Just go to Canvas. It's there for you, and you can make a copy of it and use it. So it's all done for you. You don't have to write it. You just have to use it in a useful way, okay? So I'm going to give you a whole bunch of data, depending on which adventure you choose. This is going to be a very large graph of data, and you're going to analyze that data to answer the question from the story problem, depending on which story problem you want. So you're going to build your graph edge by edge, and you're going to have special questions. You may need to write an extra method or write some code in main, not a lot of code, but obviously you'll need to understand what you're doing, and then print out some specific results, okay? So it's not a lot of code writing except in main and maybe some head scratching from time to time. So let's put it in the context of Star Wars. Yoda is node 1, the evil emperor is node 0 in a very large graph. They are probably on an island with a lot of other people. Some are following Yoda, some are following the evil emperor, okay? That's a connected component that is connected to 1, node 1, or a connected component to 0, okay? So you are trying to find the largest independent island that is not already connected to this or this. We're going to try to sway them over to either side. So you're going to have to analyze all the connected components, find which one is the largest that is not already containing 1 and not already containing 0. Okay, so you're going to have to print out some data, print out, maybe automate some of your questions, and, print out maybe by writing some code what those answers are. Okay, so because we want to know who the free thinkers are. What are the node numbers of the largest group of free thinkers? Okay. Okay, so that's kind of one of those, and we'll come back and drill into some of these other adventures so you can decide which one you want to take. But hopefully that kind of shows you kind of why and where we're going to try to apply this connected component thing. Okay, so you'll have to find somewhere out here is the biggest one, right? Which one is the biggest one that's not connected to either one of these already? Okay, okay. All right, so that leads us to our lab, which is not too hard. Lab 22. We're just going to fill in the missing code in main to print out all the vertices in the graph, okay? And then create a path instance, very much out of our homework today, and use source vertex 4, and then use the appropriate methods in the path instance to determine which vertices of the graph can be reached from vertex 4, okay? So you're really just exercising the practice problems today. And let me just take a quick show you the code, and then we'll let you get on your way here. Okay, so the node is here. The graph class is here. I'll fold that up, right? There's nothing special there. Our path class is here. Okay, and in main, you just need to kind of, here's the graph being built for you. This is me printing the adjacency list, and now you have to do the analysis of the path, okay? These are the vertices that can be reached from 4. So by default, you're just going to get, you got to print some code here, right? So you're going to have to build your graph or your path class here, and you can do that, from what we covered today, okay? Questions before I call it? All right. Thanks, everybody. Remember, don't come to class on Tuesday. I'll see you next week on Thursday. Okay. Thank you.